Hello everyone. We are going to start the discussion on the next chapter, angular momentum. So what is our aim in this chapter? Okay, we want to study um, the motion of a large body as a whole. Okay, in the chapter on Newton's laws of motion, in the unit on Newton's laws of motion, we were discussing motion of a particle. Okay, motion of a point particle. So here we want to discuss motion of a large body, okay, an extended body. So there are we can think about an extended body as a collection of a large number of particles, and in order to analyze the motion of a body, so my point is this: consider a body like this, okay, an extended body like this. So suppose this body undergoes some motion in some direction. Okay, we want to analyze this motion. So one way to look at this is you consider this body, okay, as a collection of a large number of particles. Okay, and when you study the motion of, in order to analyze this motion of a body, you look at the motion of each particle. Okay, each particle, and you analyze this particle by particle basis. But this will not work because this body contains a large number of particles. So writing Newton's equation of motion for each particle and analyzing it is it's impossible. So we want to have another way of looking at this motion of the body, and also this body need not undergo just a linear motion. It may undergo rotation also. Okay, so we want to analyze the general motion, linear motion as well as rotation motion, a motion in a general way for a rigid body. How do we do this? Okay, so there should be some method to study rotation motion also. Okay, and before going to that, let us look at an important theorem called Chasel's theorem. This was discovered by Michel Chasles, a French mathematician. So what is the idea of this Chasel's theorem? His idea is that any displacement of a rigid body, okay, just like the one I have drawn above, it can be decomposed into two independent motions. One is a translation of the center of mass. Okay, so consider the center of mass of the body and translation of the center of mass. So we look at the center of mass and look at the translation of the center of mass, and secondly a rotation around the center of mass. Rotation around the center of mass. So any general motion of a rigid body we can decompose into these two parts. Okay. First is translation of the center of mass, and secondly rotation around the center of mass. I will show an illustration of this from your textbook. Consider this figure. This is a rigid body shown here, a chair, and consider a general displacement of this rigid body. Okay, a chair is it is falling sideways like this. Okay, now the idea of Chasel's theorem is that this motion, this is a general motion of a rigid body. Okay, a large body. So here we can decompose it into two parts. One is consider the center of mass of this body. Let us say this chair, the center of mass of this chair is somewhere here. Okay, so now when you look at the new position B, the position of the center of mass is here. So when this chair falls down, we can look at it as one step is the translation of the center of mass from here to here. And secondly, the orientation of the body is not different. Here it is vertical, here it is nearly horizontal. So what happens here, there is a rotation around the center of mass about maybe this axis. It is rotated like this, okay, in this way. So this general motion falling down of a chair, we can resolve into or decompose into translation of the center of mass and rotation around the center of mass. This is the idea of Chasel's theorem. So how is it useful? Okay, in the previous unit we have been studying translation motion of a point particle. Here you can treat center of mass as a point particle. Okay, so the idea of the analysis of the translation of the center of mass is just like the translation of a point particle, a point mass. Okay, then so next part is rotation around the center of mass. So how do we analyze rotation of a body? Okay, so that's what we are going to discuss in this chapter. Okay. So in order to discuss rotation motion, so what I plan to do is, what we are going to do is, in linear motion, okay, we have a set of ideas. We introduced the idea of force, then linear momentum, and also the idea of center of mass of a body, center of mass of a large body. Okay, now identical to this one, this idea, okay, identical to this idea, I am going to introduce in rotational motion similar identical concepts. So in rotational motion, corresponding to the idea of force, we will study what is the idea of torque. It's equivalent to the idea of force. And in linear motion, you have linear momentum, and corresponding to that, here we will introduce angular momentum. Okay. And corresponding to the idea of center of mass, we will introduce the idea of moment of inertia. Okay, these three are one-to-one ideas. In linear motion, we have these ideas: force, linear momentum, and center of mass. And whereas in rotational motion, equivalent to force, we introduce torque; equivalent to linear motion, we introduce angular momentum; and equivalent to center of mass, we will introduce moment of inertia. So, okay, so this is the idea that we are going to do. So first of all, so ultimately our aim is to study the motion of extended bodies, okay, as we have shown here in the case of a chair. Okay, we want to study the motion of extended bodies. Okay, but before that, first we will look at the motion of, again, the rotation of a point particle. Okay, this is very useful to introduce the basic idea of angular momentum and torque. So we start with the angular momentum of a point particle. Okay, so let us consider, um, let's say you have a particle um, at this point. Now its position vector from some origin here is r. Okay, and this particle has some linear momentum, let us say along this direction. So its linear momentum is p. Okay, then how do we define its angular momentum? Usually we use the symbol capital L for angular momentum. It's a vector, and this angular momentum is defined as r cross p, the cross product or vector product between the position vector r, okay, this position vector r, and the momentum p, r cross p. So it's a cross product. Okay, you have studied the cross product of vectors. So what is the magnitude of this angular momentum? Magnitude of this angular momentum is magnitude of r into magnitude of p into sine of, okay, the angle, let us say theta, between r and p. How do we show the angle? The direction of r is along this direction. Direction of p is like this, so this is the angle theta. Angle between the direction of r and the direction of p. And so this is the magnitude of angular momentum L. Magnitude of r, magnitude of p, sine of the angle between r and p. So r, p, sine theta, let us say. What is the direction of r and p? For this we have to consider the plane containing r and p. So let us say this is the plane, some horizontal plane containing r and p. Okay. Sometimes this is called the plane of motion. The plane containing r and p is called plane of motion. And here, okay, so in this plane of motion, the vectors r and p lie in this plane, which is called plane of motion. Then the direction of the angular momentum vector will be perpendicular to this plane containing r and p. In this particular case, the angular momentum vector is perpendicular and directed upward from the plane of motion. Okay. So how do we fix the direction of R and P? Because if you have a plane of motion, okay, if you have this plane of motion um, containing r and p, then there can be two directions perpendicular to this plane. One can be perpendicular and upward, and the other can be perpendicular and downward, or we can say outward direction and inward direction. If I say the upward direction as outward direction, there can be downward direction also. So how do we fix the direction of r and p, I mean angular momentum vector? So this problem is equivalent to how we fix this is the same as how we fix the direction of cross product between two vectors. So we will look at it a little later. Before that, before going to how to exactly consider the direction of r and p, what is the unit of this one? What is the unit of angular momentum? Unit of position vector r into unit of linear momentum. We know that unit of linear momentum is mass into velocity, so kilogram meter per second. And from the position vector r, you have one more meter, so we have kilogram meter per second into meter, so kilogram meter square per second. That is the unit of angular momentum. So so we have to note 2 points here. Okay, one is this definition of angular momentum involves the position vector r. Okay, it means that the value of angular momentum, okay, depends not only on the motion of the particle, that is not simply on the linear momentum or the motion or velocity of the particle. Okay, it also depends on its position vector. Okay, that means it depends on the location of the particle, where the particle is located with respect to an origin. This, if I have chosen an origin somewhere here, and with respect to this origin, where the particle is located, that is important. So angular momentum simply doesn't depend on the motion of the it does not alone depend on the motion of the body, it also depends on the location of the body. Okay, so we cannot meaningfully speak about angular momentum of a particle without considering the coordinate system. So whenever I talk about angular momentum of a particle, we have to consider these two things. What is the motion, what is the direction of motion, what is the magnitude of linear momentum, and also what is the position of the particle with respect to an origin. Okay, so I will be calculating the angular momentum with respect to some origin. So what is the position vector from the origin? That is very important. What is the coordinate system? Okay, so we should keep in mind that this is in contrast to the situation for linear momentum. Okay, because linear momentum is independent of any coordinate system. When you talk about linear momentum, um, you don't worry about where the origin is, what the coordinate system is. It's independent of the coordinate system. Whereas angular momentum depends on the coordinate system. It depends on the position vector of the particle from the um, origin of the coordinate system. Okay, so that is the first important thing. And second important thing is, this is a cross product. So its direction is perpendicular to this plane containing R and P, this plane of motion. Okay, that is it. How do we, again, let's come back to the earlier question. How do we identify the direction of angular momentum? So this is the same as how we fix the direction of cross product between two vectors. So here we have to consider R cross P. So what do we do is, okay, take your, we use the right hand screw rule for this one, or let us say right hand um, grip rule, sometimes we can say. So how do we do this right hand grip rule or right hand screw rule? So we fix your right hand at the origin. Okay, extend your right hand index finger, the index finger of the right hand, towards the first vector. What is the first vector here? The first vector here is vector r, because we are evaluating r cross p. So first vector is r cross p. So imagine placing your right hand here at the origin, extend the index finger, okay, of the right hand to the first vector. Then you turn your in addition to except the thumb, the other four fingers, okay, the index finger, middle finger, ring finger and small finger, these four fingers you turn to the second vector. Okay, you turn in the direction of the second vector. So first you extend, you fix the direction of the first vector, that is by extending your index finger to that direction. Then curl or turn, okay, the four fingers, that is except the thumb, turn the four fingers, index, middle, ring finger and small finger, turn these four fingers to the second vector. And in this position, what is the direction of your thumb? That will be the direction of L. Okay, so you place the thumb right hand here at the origin, extend the index finger to vector R, then turn all the four fingers except the thumb to the second vector, that is to the momentum P, linear momentum P. Then the thumb position of the direction of the thumb gives the direction of L, that is R cross P. Okay, if this is, you consider this as some vector A, R as some vector A, P as some vector B, then this is the direction of L will be the direction of A cross B. It's the same thing. How do we the direction of A cross B, cross product between two vectors, we define or we fix by this right hand screw rule. This is called right hand screw rule. Okay, I have collected a few figures from the internet here to show this, to illustrate my point. Okay, see, look at the first figure. This is the first vector. We want to find the direction of A cross B. Okay, so this is the first vector A, this is the second vector B. Theta is the angle between A and B. Okay, so what is the magnitude of C? Modulus A, modulus B, sine theta, just like I have written here. Okay, magnitude of L is modulus of R, modulus of P into sine theta. Theta is the angle between R and P, in the same way here. Okay, so that's the first figure. So what is the second figure? See how we find the direction of A cross B. So for that, your index finger of the right hand is extended towards the first vector A. Then okay, whatever I have said, they have shown here together. Okay, so extend your index finger here, then curl all the fingers. So instead of showing all the fingers, all these four fingers, they have shown only a few. So you extend them in such a way towards the second vector B. Okay, so this middle finger is essentially extending in the direction of B, from A to B. You are turning. Then the thumb gives the direction of A cross B. Okay, look at the third figure. this idea of curling from first vector to second vector is shown here. This is the first vector. Look at the figure on the right side. That is this is the first vector u. We want to find out the direction of u cross v. This first vector u, second vector v. So you extend you place your right hand at the origin, extend the forefingers, to the first vector. Maybe instead of extending the index finger to the first vector u, you can extend these forefingers to the first vector, then turn these forefingers towards the second vector. So see the direction of turning from here to here. The thumb gives the direction of um, u cross v. Okay. Okay, I have a few more figures. Let us look at the others. Okay. Okay, this idea of is expressed again in this figure. Extend your index finger to the first vector v, then turn all the fingers, all the four fingers to the second vector w. Thumb gives the direction of v cross w. Here in this figure, we want to find the direction of x cross y. Okay, so for that, place your right hand here at the origin, extend the thumb index finger or just the four fingers to the first vector x, turn to the second vector y. So this is the direction of turning. X cross y gives the direction of, the thumb gives the direction of x cross y, which is set. Okay, and this is the same as the turning of a right hand screw. Okay, from x to y. You place a screw at the origin, you turn it from x to y. So I am placing it perpendicular to the plane containing x and y. And I have to place this screw perpendicular. If you are looking at a right hand screw, which is the normal screw that we use in most of the appliances, for fixing let's say a photo on the wall, a picture on the wall, we use a right hand screw. You place the screw perpendicular to the plane containing x and y, the two vectors, xy plane, and you turn the screw from x to y. So you are turning it, let us say, if you look from above, you are turning it in the anti-clockwise direction, right? Okay. So if you are turning it in the anti-clockwise direction, the screw will be moving in the plus z direction. Or if you look from below also, you are turning it, okay, if you look from below, the sense of rotation will be different. Anyway, if you look from above, let's consider any one position. If you look from above, you are turning in the anti-clockwise direction, and the motion of the screw will be like this, along the plus z direction. So the direction of advancement of the screw gives the direction of x cross y, which is the z direction. It's the same thing when you use your right hand grip or right hand to show this direction. Okay. Now here, suppose you rotate from the first vector to the second vector in the clockwise sense. Okay, look at this in the clockwise sense. Then the cross product points into the page, perpendicular and into the page. Okay. On the other hand, if you rotate from A to B in the anti-clockwise or counterclockwise sense, the cross product points out of the page. The idea is, if you have two vectors on this page, on this plane, on your screen, then there are two directions perpendicular to this plane, out of the page, out of the screen, towards you. Okay, towards you. Second is into this page, away from you. Okay, so how do we get this? So this right hand screw or this right hand rule that we have illustrated so far, here or in all the previous figures, the rotation is in the counterclockwise sense. Look at this figure on the left. You are extending your four fingers or the index finger to the first vector, and you are turning from the x to y in the counterclockwise sense. Okay, if you look from above, it's in the counterclockwise sense. So the thumb is extending out of the page. Okay, the z direction. If this page represents or the screen represents xy plane, the thumb will be towards you. Okay, that is it. Okay. So on the other hand, if you are rotating from clockwise direction, Okay, you have to imagine it here. If you are rotating in the clockwise sense, how do you find A cross B here? Again, extend your index finger to A, then rotate all the four fingers to B. So in that case, the thumb will be pointing downward into the page. Okay, so the rotation is in the counterclockwise sense. Then it will be out of the page. If the rotation is in the clockwise sense, it is into the page. Okay, you have to practice it, only then you will see this point. And finally, I have summarized all these points in the last picture here. The vector product of A and B written as A cross B produces a third vector C whose magnitude is, okay, C equal to A cross B. Its magnitude of C is modulus A modulus B sine theta, where theta is the angle between A and B. Okay, and let us look at these two figures. Okay, see A cross B. As I said, place your hand at the origin, for right hand at the origin, extend the four fingers to the first vector A, turn it to the second vector B, then the thumb gives the direction of C, which is equal to A cross B. Suppose you find B cross A. What do? Place the thumb, right hand here, extend the four fingers to the first vector, which is B in the case of B cross A. Turn the four fingers to the second vector, which is A. So what's the direction of B cross A? Downward. So this is the idea expressed in the previous figure. That is, if you turn from A to B in the counterclockwise sense, that is in the first figure here, counterclockwise sense, then the direction of A cross B is out of the page, out of this plus Z direction, we can say. If AB is in the XY plane, this is in the plus Z direction. Whereas if you rotate from first vector to second vector in the clockwise sense, whether A cross B or B cross A, if you are rotating in the clockwise sense, it will be in the, if AB is in the XY plane, the thumb will be in the minus Z direction, perpendicular into the page. Okay, so the minus C, B cross A is simply minus C. Okay, if you find A cross B, its direction will be plus Z direction. I am assuming that AB is in the XY plane. So this is in the plus Z direction, whereas B cross A is in the minus Z direction. So B cross A is simply negative of A cross B. Magnitude will be the same. Okay. So this is the way we identify the direction of A cross B. And since the definition of angular momentum contains cross product, okay, angular momentum of a particle contains a cross product. It is R cross B. The direction of angular momentum is obtained by the right hand scroll rule. Okay, right. You extend your index finger, place your hand here at the origin, extend the index finger to the, or maybe the four fingers to the first vector R, turn them to the second vector, which is linear momentum P, then the thumb gives the direction of L or R cross B. Okay. So I will stop here with this idea. In the next video, we will continue the discussion. Thank you.